Okay, here we are with our first lecture for Chapter 7. It's Quantum Theory and the Electronic Structure of Atoms. We're going to be talking about electrons primarily. Math and the numbers and the energy get really, really small with this kind of stuff. And some of it, quite honestly, is a little bit out of my grasp, but I can show you how to use these equations and the things we can calculate with them. So let's hop right into it here. If you've done a physics course or even a good physical science course, I hope this is old news to you. Waves have a number of pieces that we can name. One's the wavelength, one would be the amplitude of the wave, and then the frequency of the wave. So wavelength is commonly denoted with this Greek symbol lambda. It's the distance between identical points on successive waves. So here they go from the peak of one wave to the peak of another wave. That's its wavelength. So you see this top wave has a very long wavelength. The bottom wave has a very short wavelength. You could do the same thing for maybe trough to trough, or midpoint on the way down to midpoint on the way down, kind of however you wanted to do it. That's a wavelength. Our amplitude is going to be vertical distance from the midline of a wave to its peak or its trough. So our amplitude could be this, or it could be this. This would be, if you were talking about waves on the ocean, how tall the wave would be its amplitude. And then our frequency. And our frequency is denoted with V. And I'm struggling with this because I learned it as lowercase f, which was wonderfully logical for me, but you should probably learn it as V because that'll be the equation you get in your AP test. So do your best there. I remember Mr. V frequently visits my room, so I kind of have my little mental jump with that. However you want to do it, do your best there. But frequency is the number of waves that pass through a particular point in 1 second. We normally measure these in hertz, Hz, and that's 1 cycle per second. And so that's frequency. When you tune into a radio station, 97.9, it's a frequency that you're tuning into to get those radio waves to your radio. So that's kind of a cool application to frequency. So there's some background physics stuff that hopefully is not too bad. So our formula for speed, they're giving us the symbol mu. It'd be nicer if we could do v for velocity, but we don't. We have v for frequency, so it just, don't want to say it gets worse, but it gets worse. The speed, mu, of the wave is equal to your wavelength multiplied by your frequency. And so that's the first equation you're going to want to know. We're going to use it a lot. So 1873, a long time ago, Maxwell proposed that visible light consists of electromagnetic waves, and I think we found that very probably is the case. He proposed that we have two components to the visible light that kind of comes to Earth, from the sun, or maybe visible light that we create. We have an electric field component that travels as a wave, and then perpendicular to that, we have a magnetic field component that travels as a wave. And so this is kind of how we believe light behaves. Electromagnetic radiation is emission or transmission of energy in the form of electromagnetic waves. So a lot of the stuff we deal with is going to be electromagnetic waves, and I'll show you this big chart of it in a little bit. Here's something you want to commit to memory. Speed of light in a vacuum. How quickly does light travel? It's 3 times 10 to the 8th meters per second. You're going to use that a lot for your speed for the equation. They'll ask you about light. And even though you and I, don't really exist in a vacuum, when we're dealing with speed of light in our classroom or lab or whatever, we're going to pretty much go with 3.0 times 10 to the 8 meters per second because the differences will be pretty negligible. So then here's your formula for any electromagnetic radiation. Again, we said, our wavelength times our v was frequency would give us our speed. And so now we're substituting speed in as c being our speed of light in a vacuum, 3.0 times 10 to the 8 meters per second. So once you've committed that to memory, you can solve for either of these unknowns as long as I give you one, and the book will give you a lot of opportunity to practice with that. So here is your electromagnetic spectrum. This little teeny tiny sliver of gray, this is all that you and I are detecting with our eyes. Here's 400 nanometers to 700 nanometers. We'll be converting a lot between meters and nanometers, so you just as well know this now. There are 1 billion nanometers in a meter. The other way to say it is in 1 nanometer, there's 1 times 10 to the negative 9 meters. You're going to use that a lot, so just letting you know. Anyways, here you have your wavelength. You can see that your wavelength starts very, very short, and it increases to very, very long wavelengths here. And here you can see your frequency starts out at a very high frequency, goes down to a very low frequency. And here's gamma radiation, X-rays, ultraviolet would be sun lamps, that kind of stuff, things that are heating something, and then the light from the sun, of course, UV light that gives you sunburns would be ultraviolet spectrum. Then we move into visible. Then we go into infrared. That's like the thermal imaging cameras and security, heat lamps, that sort of business. As we move to an even longer wavelength, we get to what we use to use in microwave ovens. Then we get to some cell phones, the frequencies that they're transmitting at, FM radio, and then even longer AM radio. Sometimes you can tune into AM radio stations that are quite a ways away. So that's electromagnetic spectrum. So here's our first problem. If we had a photon, and a photon is the particle of light, I guess you could say, that's coming in from the sun all the time, has a frequency, so that would be, frequency, lambda. No, lambda's wavelength, sorry, frequency was V of 6.0 times 10 to the fourth hertz. Convert the frequency into wavelength, that's lambda. Does it fall in the visible region? And so we set up our equation of our wavelength, what we're trying to solve for, times our frequency, which is our V, 6.0 times 10 to the fourth hertz, is equal to our speed of light, which I said we should memorize, at 3 times 10 to the 8th meters per second. So they rearranged their equation right away for lambda. Go for it, whatever you're comfortable with. And then we find that we have meters per second divided by hertz, which is oscillations per second. So we should be left with like meters, basically, as a unit. And so we get our wavelength to be 5 times 10 to the third, 5,000 meters. But they ask for it in nanometers, so we do have to convert it. That would be 5 times 10 to the 12th nanometers, because there's a billion nanometers in a meter, so there's 9 more zeros. So we get that answer for nanometers, and that's how you would do a problem like that. And you'll get to do a few. So then you have to see if it falls in the visible region. You have to go back to the graph I showed you before. You have to look at where 5 times 10 to the 12th is for lambda, and you find that you're 10 to the 11, 10 to the 12. It's more likely something like an AM radio station than it is something you can see with the human eye. So, all right, mystery number 1, mystery number 2. Heated solid problem solved by Planck in 1900. When solids are heated, they emit electromagnetic radiation over a wide range of wavelengths. You can think of perhaps a blacksmith pulling an iron out of the fire, and the iron is glowing like white or orange or red. When, of course, when it's cool, it's sort of a dull gray color, and that's emitting visible electromagnetic radiation. So we've known that this happens for really a long time. But radiant energy emitted by an object at a certain temperature, what Planck found was that it really just depends on the wavelength, not so much other variables, really just the wavelength of whatever that radiation is going to be proportional to our energy. So our energy, he found, was emitted or absorbed in discrete units, and he called those quantum. We're going to deal with this word a lot, quantum. Quantum basically means packet or unit. So it's like level 1, level 2. There is no level 1.5. That's the idea of quantum, and you're going to see this a lot. And so basically what he found for us was that energy emitted by light or a photon is proportional to a constant that he derived, so it was named after him, Planck's constant, that's h, times v, which was our frequency. And so here's h, 6.63 times 10 to the negative 34th joule seconds, and you're going to use that as well. And so it makes it pretty easy, because we can take v and we can solve for the speed of light and wavelength from the equation that I showed you right away, and then we can work that back to find the energy of a single photon if we started with information as simple as its wavelength. So it's pretty useful to use these two together. Mystery number 2 is the photoelectric effect solved by Einstein. This is where electrons get weird. We were kind of cool with them being particles for a while because they behave like particles. Then we did other experiments where they kind of behave like waves. And so the only way that we can really bring this to our understanding is to accept the idea of wave-particle duality, which is that electrons are particles, yep, and they're waves, yes, and they're both at the same time. So the way we think of large objects, like a wave on the ocean or a cue ball as a particle, they don't work that well when we get to the level of electrons. They just don't behave that well. So we say light has both the wave nature and the particle nature. And we say that particle of light is what we call a photon. So here we have light coming in and striking a metal plate. And then it bounces off the metal plate and it reads a voltage for us. And so here we have H, Planck's constant, V, frequency, coming in. And then as it closes the circuit for us and is attracted to this positively charged rod here, we get kinetic energy based on how quickly it's coming in. And so from that, Einstein was able to derive this equation that Planck's constant times our frequency is actually equal to the kinetic energy of the particle plus the work the particle is doing. So that's an equation we'll use a little bit this chapter. Then you can, of course, solve for kinetic energy, just a little bit of algebra work there to switch some things around, and you can solve for kinetic energy of a particle. W is the work function, and the work of an electron depends on how strongly electrons are held to the metal. So that's where we have the photoelectric effect. Alright, so if we look at a problem like this and it says copper is bombarded with high energy electrons, it'll emit X-rays, which would be kind of crazy. Calculate the energy in joules associated with the photons if the wavelength of X-rays is 0.154 nanometers. So we want to get to E, energy, and we're starting with wavelength lambda. And so we can say if energy is equal to Planck's constant times our frequency, then we need to find frequency. And we learned earlier that frequency was equal to speed divided by lambda. That's the first equation I gave you. So we can substitute those two in. Now we can use lambda here, and we have speed here. I said be worth memorizing, 3.0 times 10 to the 8th meters per second. And we have h, which is Planck's constant. And so we plug this in. Here's Planck's constant. You'd get that from an equation bank or perhaps memory if you've got it memorized. I don't quite yet. And then your speed of light, which you'll want to memorize. And then this, which they gave you in the equation. And you'll look that meters cancels out here, seconds cancels out here. You're left with the unit of joules. And when a question asks you for energy, that's a really good place to be. So seconds cancels, meters cancels, energies in joules. You note that it's an incredibly small number, 1.29 times 10 to the negative 15. That's 14 zeros. That's really, really, really small energy. But it makes sense because we're asking about photons, which are really, really, really small particles. So that was kind of the wave side of things. Let's look at the particle side of things. This is a weird little experiment. Pass a bunch of high voltage through a gas discharge tube, and it's going to fire particles at this sheet. And the sheet has a teeny tiny slit in it. So some of our particles are going to travel through here. This will be particles and waves, I guess you could say. And they'll travel along here as one beam that we would view it as. But if you run it through a prism, it will be separated into its individual line spectrum. And what we found is that depending on the gas that you're going to be firing these particles from, they all give different line spectra. So it's sort of odd. We can use this method, although it is a little time consuming, to identify what elements are in a sample based on the line spectrum they give off, because they all are going to, hopefully this is the right word, diffract a little differently. So here's the hydrogen atom. It's 400 to 700 nanometers. That's the visible range, of course. It'd be a little hard to take a picture of something we can't see, and it's nice to have color. So we have one purple line, blue line, green line, red line. That's hydrogen. And if you look at all these different metals, you'll note that they're all very different. You can see barium has quite a few lines in the red, and a lot of others don't have those three right away. And so we can use this to kind of tell what's what. So alkali metals here, alkali earth metals here, and you can tell a little bit of similarities there. Metals, they're sort of all over the place, as metals normally are, and then gases here at the bottom. So all different line spectra. Kind of crazy. So we're going to talk about different models of the atom. We kind of just jump right to the end of the story with our present day understanding, which is fine, because in Gen Chem you kind of learned how we got here. But Bohr's model of the atom, he started with this hydrogen atom idea, that electrons can only have specific quantized energy values. So n equals 1, that's a level 1, principal energy level 1, principal energy level 2, principal energy level 3. There's no energy level 2.5 or 1.3 or anything like that. He also said light is emitted as electrons move from one energy level to a lower energy level. Hopefully you remember in Gen Chem we went into like a dark room and we crushed wintergreen lightsabers in our mouths, and we could actually see the lightning coming out of those wintergreen lightsabers, and that was because when you put so much force in here, you force electrons to change levels, and when they do, they emit that light. And so that's one energy level to a lower energy level. That's the reason lightning is actually visible to us. So now we get this kind of confusing equation. The energy that's proportional to n, which is our principal energy level, this is locations of electron probable existence, is equal to negative RH, which is going to be a Rydberg constant, multiplied by 1 over the n squared, and the n would be, again, its principal energy level, 1, 2, 3, whatever that would be. So principal quantum number, 1, 2, 3. You might remember something like 1s2, 2p6, 3s2. Those are the principal quantum numbers, what we're using when we're describing that electron location. So our Rydberg constant is RH. That's something that has to be given to you. 2.18 times 10 to the negative 18 joules. And so with that we can look at electrons dropping down to different levels. Electrons, chemical bonds, they want to be as stable as they possibly can. So here we have the energy that is released when this electron moves from a higher energy level to a lower energy level is equal to h, which is going to be our Planck's constant, times v, which is going to be our frequency. And it's the same case here for this one that drops down multiple energy levels. Of course, this small jump would release a little bit of energy. This jump here would release a lot of energy. And so that's what we see. So the energy of photons are equal to the energy final minus energy initial, kind of like the stair-step thing. And that's how we get this equation here. We just kind of start with the final and our initial, and we can solve for it. So because it's sort of like a state function, it depends on the beginning and the end. We take our Rydberg constant and our initial minus our final, and we get our change. So this shows you the energy level 2 to energy level 1, energy level 3 to energy level 1, energy level 3 to 2, and then here is your spectrum region that those would fall into. I don't think you need to memorize the names of these different series. I haven't, so I hope you don't have to. So we could use this for something like this. The wavelength in nanometers of a photon emitted by a hydrogen atom when its electron drops from n equals 5 to n equals 3. And so our energy of a photon is going to be equal to our change in energy when that electron actually makes the drop. The Rydberg constant is given to you, and then we have our initial n and our final n. And so those aren't too bad. Here's the Rydberg constant that you'd have to have given to you, and then here Ni, the initial level, was 5, and so n squared, 5 squared, would be 1 over 25, minus n2, which was 3 squared would be 9. And so then it's really not too bad. We pretty much got it. The energy of the photon is negative 1.55 times 10 to the negative 19th joules. Again, it's a very, very small number because it's just one photon. So that's energy, and just that was a pretty good accomplishment on its own, but they asked us for wavelength. So in order to get from energy to wavelength, now we've got to pull back another old equation which we used a few slides ago, which was energy equals h, Planck's constant multiplied by our speed of light divided by our wavelength. We've got energy here, so we can plug that in here, rearrange the equation for wavelength, or you can plug your values in and solve for wavelength later, whatever you prefer. They rearrange the equation first, which is fine. And then they plug in Planck's constant, which we knew, the speed of light, which is 3.0 times 10 to the 8th, divide by the energy of the photon that we calculated, and we have a wavelength in meters. So be careful, because it would be a downer to do all that work and get the answer wrong. You'll note that they didn't show their conversion here, but their wavelength solved for meters, and their question asked for nanometers. So you'd still have to make that jump to multiplying by 1,000,000,000 to get to nanometers. So don't do all that work to trip at the very end. Track your units, show your work, and you're going to make out all right. If you don't show your work, you're going to be toast. Why is electron energy quantized? That's a good question. I don't know. But I guess de Broglie figured it out in 1924. He said that the electron's both a particle and a wave. We are inclined to believe him. Here's the equation he came up with. 2 pi r equals n times lambda, and then lambda is equal to our Planck's constant divided by our mass, and our u, which would be our velocity. So u is the velocity of the electron, m is the mass of an electron, super, super, super small. And so you can use this to get the de Broglie wavelength for a ping pong ball. If we did something that had a mass that was a little more measurable than an electron, 2.5 gram ping pong ball traveling at this velocity, you'd find that wavelength equals h divided by m and mu, which is our velocity. H is in joules per second. Mass has to be in kilograms to use this equation. And then our velocity is in meters per second, which is pretty standard, so that's not too bad. And so then here's Planck's constant again, which we've used a lot already. Then we're dividing that by our kilogram mass here, 2.5 grams. You'd have to divide by 1,000 to get your kilogram mass, multiplied by 15.6 meters per second. That's your velocity here. So you get your wavelength to be 1.7 times 10 to the negative 23rd nanometers. So if a ping pong were to be traveling, it would oscillate just a little teeny tiny bit. If you look at 1.7 times 10 to the negative 23rd nanometers, this is indescribably small oscillations. I don't know how else to say. 0.00022 times billionth of a meter. That is an incredibly small oscillation. So, but it's a wavelength. So that's where we'll stop. We'll talk about lasers next time. Thank you.